Way back in the beginning of Organic 1, I said we start by learning functional groups because that's the foundation of everything we'll do. And as I explained in the last video, we're talking about Group 2 now. I didn't call it that, but we're talking about Group 2 now. We've already talked about alkyl halides and substitution and elimination of alkyl halides, but now it's time to talk about alcohols, ethers, epoxides, sulfonate esters, sulfides and sulfonium salts, and ammonium hydroxides, quaternary ammonium hydroxides. Yep, Group 2. Group 1, done. That was last semester. Group 2, now. And then we'll focus on those guys later. We said the first functional group we're talking about this time is alcohols. We got to remind you of how to make alcohols and tell you what alcohols can do once you make them. These reactions are old ways to make alcohols. They all start with alkenes. You could also do substitution of an alkyl halide. So these are addition reactions. You could also do substitution to make an alcohol. There are a few other reactions to make alcohols, these bottom three, that we will talk about in the future of this semester. We don't know them yet, but there are a lot of ways to make alcohols. We know the top ones, but not the bottom ones. We'll get there soon. Reminder of how the top few reactions work. Here's an alkene, and I react that alkene with acid and water. You need to know what kind of intermediate it goes through. It goes through carbocation. It would go through this secondary carbocation. Yeah. Water attacks, water cleans up, makes an alcohol. Additionally, that carbocation can rearrange to make this carbocation. Water attacks, water cleans up. Yeah. Okay. That would end up making these two products. Because you went through a carbocation, the stereochemistry should be racemic at that asymmetric carbon, and this is not an asymmetric carbon. So you get two constitutional isomers. You get three actual products, the R and S version of this guy, and then this guy is so low he doesn't have R or S, no asymmetric carbon. Yeah? How is acid and water different from mercury? Mercury still does Markovnikov, yeah, but no carbocation, therefore no rearrangements. So we get this product and this product only as our only constitutional isomer. Yes, it would be racemic because mercury does not give you specific stereochemistry. So we get one constitutional isomer, those two stereoisomers. And how is water and acid different from mercury, different from boron stuff? Boron stuff, followed by hydroxide and peroxide. That gives me anti-Markovnikov addition. Also, no carbocation because it goes through an organoborane. It gives you a CN addition product. That's my actual product. That's not an asymmetric carbon. Neither is that. Neither is this. There are no asymmetric carbons in this molecule. So while it does give syn addition, there's no need for me to designate that in this molecule because it doesn't matter. So Markovnikov, anti-Markovnikov, all of these are hydration of alkenes. All of these are classified as addition reactions. Yeah? Okay. How would we make alcohols? Well, one way that we know how to make alcohols is starting with an alkene. So if we're trying to make an alcohol, that alcohol could be made from, I could imagine, this red alkene or this blue alkene. Either one of those are alkenes that could be used to make that alcohol. But is one a better choice than another? Yes. Who's the better choice? The red one. Why is the red one the better choice? Because this is secondary. This is secondary. If you want to do Markovnikov, which side gets the H, which side gets the nucleophile? Oh no. They're the same. The secondary versus secondary, these sides are equivalent, so there's no difference in Markovnikov and anti-Markovnikov on the blue thing. Would you get any credit for putting the blue thing? Yes, but not as much as if you put the red thing, Because the red thing, you definitely need to make Markovnikov or anti-Markovnikov. So you need boron, and you need hydroxide and peroxide. Yeah? This synthesis gives you the most points, all the points. The blue synthesis with Markovnikov stuff or anti-Markovnikov stuff, no matter what reagent in the blue, you're going to get some of the product you want and some of the product you don't. In fact, if you add acid and water, you're even going to get a third product from a rearranged carbocation, so you would actually get a little bit less credit for acid and water on the blue carbocation. All right, what about the other one? This says 2 ways. I could imagine this alcohol, this alkene, with the rest of that being the rest of the molecule. Yeah. I could imagine synthesizing from this alkene. Yeah? Yeah. With the purple alkene, do I want Markovnikov or anti-Markovnikov? Markovnikov. Do I have to worry about rearrangements with that purple? Uh-huh. That means I definitely need mercury and water and sodium borohydride to follow up. In the blue one, do I need Markovnikov or anti-Markovnikov? Anti-Markovnikov. The only reagent for that is boron, hydroxide, and peroxide. Yeah? That's reminding you how to make alcohols out of alkenes, and prior to now, we have done plenty of syntheses of alcohols starting from alkenes. Okay, what if you don't have an alkene? Well, what if you're starting with an alkyl halide? This is a primary alkyl halide, and the flowchart says SN2. SN2. Woo, I almost missed. I did miss. Try again. SN2. We get this product where the OH took the place of the Br. And why did we swap around the D and the H? Because SN2 says inversion of configuration. So I did SN2 with hydroxide as the nucleophile. I got an alcohol. Yeah? This hydroxide can work with a secondary alkyl halide if the temperature is low enough, and it's helpful if the solvent is aqueous. We didn't talk a ton about the solvent, but yeah, you can do hydroxide substitution, SN2, on primary and methyl substrates easily, and on secondary if the conditions are favorable, meaning low temperature and aqueous solvents are helpful. Okay. We made alcohols like this. What does this do? This is an alkene, so it must be another addition reaction. But I said it makes an alcohol. Why didn't we talk about it before? Because it makes a diol. It makes 2 alcohols on neighboring carbons. A word for 2 alcohols on neighboring carbons, or 2 anything, on neighboring carbons is vicinal. Vicinal means 2 groups on neighboring carbons. Whatever those groups are, they are vicinal. So this is a vicinal diol. There's another term that is also used to relate when there are 2 things of the same type on the same carbon. That's in reference to the Gemini twins. It's a geminal diol if this were 2 OHs where the X's are. So vicinal is a term to represent relationship of 2 groups to each other. 2 OHs on neighboring carbons is a vicinal diol. It's a geminal diol if it's 2 OHs on the same carbon. That's geminal. The product of this reaction is actually vicinal. There's a reason I take a minute to explain that. Yeah. That's if I use cold dilutes KMnO4. Hot reflux in KMnO4 does something different. Remember, a hot reflux in KMnO4 does the same thing as ozonolysis with oxidative workup. Is there another reagent that we could have used besides KMnO4 to get this geminal, to get this vicinal diol? Yeah, there is another something. That's osmium tetroxide. Osmium tetroxide and peroxide would give you a vicinaldiol, the exact same vicinaldiol. These reactions do syn addition. So on this cyclohexane, that means both OHs are pointed the same direction. Syn addition. That's the recap of the old stuff. Here comes the new stuff. What all can alcohols do once you create them? Alcohols can act as acids. Alcohols have a hydrogen that's kind of acidic, pKa 16-ish. Alcohol's kind of acidic, so you can take an H off of them if you want to. You can do substitution. What two mechanisms do you think they might do? Maybe like, SN1 or SN2. Yeah. They can do elimination. It's called E1 or E2 mechanisms. In alcohols, it's called dehydration because you're always losing a water molecule when you do an elimination. They can do oxidation, which is a special type of elimination. We'll talk about them. They can act as nucleophiles to make esters, organic esters. That's our normal esters that we've talked about, or inorganic esters. So an organic ester is carbon double bonded to an oxygen, single bonded to an oxygen with an R group. An inorganic ester is some other element that X is not meant to represent a halogen, but some other element in the center surrounded by oxygens, well, with 3 oxygens around it, with a carbon group on one side and a carbon group on the single bonded oxygen side. It's called an organic ester when it has carbon. It's called an inorganic ester when it has something like sulfur, something like phosphorus in the center down here. Yep. Alrighty. Alcohols can react as acids. What bases are strong enough to deprotonate an alcohol? You need a base that will favor products at equilibrium, a base that's strong enough to deprotonate an alcohol. You know of this acid-base chart. It's somewhere scrambled around in that head of yours, I hope. Here is an alcohol. And below this, these are the acids up top. Below this on that handout, all the acids, all the bases to the left can deprotonate an alcohol and favor products at equilibrium. Can hydroxide, that's what's below here. Hydroxide, can hydroxide deprotonate an alcohol and favor products at equilibrium? No, it's too weak. An alkyne with a minus can, hydrogen with a minus can, a nitrogen with a minus can, an alkene with a minus can, an alkane with a minus can, but hydroxide and everything weaker cannot deprotonate an alcohol and favor products at equilibrium. Yeah, there's a reason this chart is in this order. So, we said a nitrogen with a minus can, that's nitrogen with a minus. We said a hydrogen with a minus can, that's hydrogen with a minus. This is something that's not on our list, that's solid sodium metal. It's a weird little reaction how that bottom one works, and we're not going to draw it, but if you ever see something bizarro like that in an ACS book, on an MCAT test, or on a DAT or something like that, this metal, with its one little electron, does some radical stuff to deprotonate that alcohol. Okay. Let's get into the real stuff, the stuff we're worried about this semester right now. That's the major focus of this first bit, this first unit. That's substitution and elimination of alcohols and other groups. So starting with substitution and elimination of alcohols. Here's an alcohol, and I'm adding HBr. Remember I said alcohols have terrible, horrible, no good, very bad leaving groups. But you can make them a better leaving group by protonating them and making that O positively charged. Turn that oxygen into a water that's connected to your carbon backbone. So let's do just that. Let's protonate our oxygen, like so, to make an O with a positive charge and 2 hydrogens connected to our carbon backbone. That's turning my OH into a better leaving group. OH is a terrible, horrible, no good, very bad leaving group. You got to turn him into a better one. And acid is a great way to turn an OH into a better leaving group. Protonate him. if you have a secondary or tertiary alcohol and you add a reagent like HBr, you're going to do a substitution reaction. That's an S. If it's secondary or tertiary, those things make reasonable carbocations. So you're going to do SN1. Have we seen primary or methyl carbocations? Not so much. They're still going to do substitutions, but they're going to do SN2. So this alcohol is a secondary alcohol. That secondary alcohol going to do SN1, which means protonate my leaving group, because he's terrible, horrible, no good, very bad. And then now that water acts as the diva, and that diva leaves behind a carbocation. That carbocation can be attacked by the bromide that's left over from your HBr. So that bromide in high concentrations going to attack your carbocation and make you an alkyl halide. Last semester, we turned alkyl halides into alcohols. This semester, the very first reaction we talk about is turning alcohols into alkyl halides. Yeah? You choose conditions that favor one over the other, depending on where you want to go. All right. So, any red flags? Anything like alarm bells ringing in your heads? Is this my only product? No. SN1, I went through a carbocation. And that carbocation can and will rearrange. Let's draw that rearrangement. So this was our carbocation. What kind of shifty shifts can it do? Yeah, you heard me. Shifts. What kind of shifts can it do? It can do a hydride shift to get me a tertiary carbocation like that. It could also do a ring expansion. 1, 2, 3, 4, 5, 6, 7. A new bond being made between 2 and 7. Who gets the plus charge? Who was the loser? Carbon number 3. So you might say, why would I rearrange this secondary carbocation to become another secondary carbocation? Because a 6-membered ring is more stable than a 5-membered ring. So you can shift secondary to secondary in this case because you are becoming more stable. A 6-membered ring is more stable than a 5-membered ring. Okay, so back to the top. Bromide attacks that carbocation, and you get this. And then to the 6-membered ring one, bromide attacks that carbocation, and you get this. The 6-membered ring, carbon number 3 has a Br, carbon number 2 has carbon number 1. Okay, so as is usual, we say, what about the stereochemistry? This guy went through a carbocation, and this is a brand new asymmetric carbon. So that's really 2 products that should be created. That's a little squiggle there. Remember what a squiggle means? Squiggle means both dashed and wedged products exist. And that squiggle is representative of both. Yeah? What about in this top red product? Squiggles? No. No asymmetric carbon. So no squiggles. And in this bottom blue product, we have 2 asymmetric carbons. Carbon number 3 and carbon number 2. Carbon number 3 used to be a carbocation, so that one should be racemic. Carbon number 2 also used to be a carbocation, so that one should be racemic. So those 2 wonky squiggles right there really represents how many products? 4 stereoisomers. A pair of enantiomers and another pair of enantiomers. 4 stereoisomers. I won't always draw them all, but I'm going to do it right now. There is one pair of enantiomers. Here's the other pair of enantiomers. Those 4 compounds are all created in that mixture. So this reaction creates 3 constitutional isomers, but 7 actual products. Cool, that's a lot. Yeah, wasn't it fun? That was so fun. How about some more? Look, it's an alcohol. It's a tertiary alcohol. Tertiary alcohols with acids like HBr do SN1. Okay. This says propose a mechanism to make these 3 products. So you're going to do an SN1 mechanism to make those 3 products. I have faith in you. I think you can do this. I think you should do this. And I think you should show it to me. Okay. So conversion of alcohols into alkyl halides is going to need an acid. An acid like HBr and HI, those 2 work well. You're going to turn your OH into a better leaving group, make it a water. If it's a secondary or tertiary alcohol that D is going to leave, make a carbocation, then I or Br attacks. Similar but different, it's just simultaneous. Do SN2 if it's a methyl or primary alcohol. HCl does work, but it often requires a zinc catalyst. The reason being, HCl is not so good at making making an OH into a water leaving group. Instead, the OH attacks the zinc and makes a better leaving group that way. It's a different way to make the OH a better leaving group. It's a catalyst. It's just a different way to make the OH a better leaving group, and then Cl is going to attack just like Br and I did. Whether it's SN1 or SN2, it doesn't matter. Okay, these things are special little reagents that can be used on methyl, primary, and secondary substrates. Why those and those only? Because it's going to do SN2, and SN2 only. These little things down here. SOCl2, we're going to call that SOCL, and PBr. This also could be PCl, PCl3, PBr5. Yeah, a lot of little reagents that have phosphorus and a halogen, and SOCl2 is really kind of the only one. But phosphorus and some halogens, they're going to do SN2. Those reagents are generally added with pyridine. Pyridine is a weak base. What is pyridine? Pyridine is a weak base. It's an amine-containing compound. This nitrogen down here is the weak base of your pyridine. Let's see how that one works. Let's see how these things work. So HBr, HCl, and zinc, HI, those are all acids. Substitution under basic conditions, that's this SOCl2 and pyridine, PBr and pyridine, pyridine, weak base. So we are not going to protonate and make a better leaving group. We have to do something else to make a better leaving group. And with SOCl2, that something else is attack the sulfur and bust out a chloride like that. We get this. Sulfur, oxygen, chlorine, positive. Nothing happened at that carbon, so that deuterium stays wedged, at least so far. And what is pyridine? Pyridine is a weak base. So you use that weak base to clean up the hydrogen on the alcohol OH that you attacked. Nope, that's an oxygen. SOCl. And then from there, the chloride that you kicked out comes back for revenge. This is a primary alcohol, maybe something I should have said in the beginning. Primary alcohols do not make carbocations, so we're going to do SN2. Pyridine and SOCL, pyridine and PBr, they only do SN2 anyway. But chloride attacks from the back, kicks out SOO, SO2, and a chloride. We get chloride over here, SOO. That's a gaseous product, and so that's very nice as far as equilibrium is concerned. Entropy favors making gaseous products because that gas can just escape out of your reaction flask. So this is a very efficient reaction, making your product very easily. What did I do down here? I did SN2. And SN2 gives you inversion of configuration. So because it's SN2 and inversion, I get a deuterium pointed backwards instead of forwards in this one. Because alcohol, the OH, was my highest priority, this was an S enantiomer. Because the nucleophile that took the alcohol's place is my highest priority, that means my product should be an R enantiomer. Is it? Yeah, it is. So that's confirmation that I drew this thing correctly when I changed from S to R if my priorities didn't shift. Whew. That's Sokol. Sokol, I should have told you his real name. His real name is thionyl chloride. Thionyl chloride and phosphorus tribromide. They do SAN2 only. The alcohol attacks the big atom, sulfur or phosphorus, ejects a halogen. When the alcohol attacks, the pyridine is going to clean up so that you have a neutral substrate. From that neutral substrate, that's where your chloride or bromide attacks to give you your SN2'd product. Ta-da! Yeah, I didn't show you the PBR mechanism, but it looks just the same. You should check it out on your own. All right, that's alcohols, their beginning reactions as acids, and substitutions. Next, we'll move on to alcohol eliminations.